Hola, buenos días. Guten Tag, bonjour, buongiorno, calimera, supravat, ausgangstag. I can keep going. This is wonderful to see all of you from different parts of the world, and it's a pleasure to talk to you here. And I'm here to tell you a story. We're all part of the IEEE Magnetic family, as you know. So, like you, I am thankful to the IEEE Magnetic Society that has enabled me to come here and speak to you. And the story that I'm going to share with you is about anisotropy, magnetic anisotropy. It's as fundamental as magnetism that we want to talk about.
It's important to be able to tune anisotropy, understand it, measure it. So these are the things that I will talk about. And also, I will show you that specifically how magnetic nanoparticles, especially anisotropic nanoparticles, can be used for biomedical applications. Professor Sarah Mezetic is going to give extended lectures later on, and she'll talk more about various types of biomedical applications of magnetic materials. So first, let me say that I would like to acknowledge various sources that have funded our work, and especially the IEEE Magnetic Society that has enabled me to give lectures here as well as around the world. And one of the reasons I started off with Spanish is because I just was there a few days back, and I'm on my way here. All right, so you are the chosen ones, so I don't need to sell the society, the IEEE Magnetic Society, but I would urge you to go to the website here, which is cut off for some reason, and get more information you would like and pass it on. Make sure that you have some of your friends join the society. You know that there are lots of advantages. One good reason is, of course, if you're a member of the IEEE Magnetic Society, you get discounted registration fees for the two biggest conferences in magnetism, the MMM and the Intermag. That's one good reason for all of you to join the society. And let me also take this opportunity to welcome you to my city of Tampa, and my university, University of South Florida. We are a pretty large publicly funded university. We are one of the 12th largest in the country, in the United States, 47,000 to 48,000 students. And something unique about my department, I don't know why the bottom is getting cut off. Why is it? So something about my department, which you see here, is that we offer a PhD in applied physics in the state of Florida. This is unique to the state of Florida. There are other big universities in Florida, and it turns out that we offer a PhD in applied physics. And of course, when you think of Tampa, you think Florida, you think beaches, right? If you remember Florida, it's a peninsula, water on all three sides, and Tampa is on the Gulf Coast, on the Gulf of Mexico. And we have the best beaches on the Gulf Coast, not the Atlantic side, all right? This is not me telling you. It turns out that late spring every year, there comes out a review of all the best beaches in the country, and Clearwater Beach, which is part of Tampa Bay, is always #1 on the list. So if you want to stay close to the best beach in this country and get a PhD in applied physics, we are the only choice. So please pass this along to your friends so that we would love to have applications from around the world for a graduate program. I would like to also acknowledge it's frozen. Apologize for this technical glitch here.
Sometimes it gets jammed up with the Zoom.
We'll go to slide number 3, please.
Yeah, you just have to keep moving. I'll
Okay.
try to figure it out.
All right. Yeah, I should have used the computer. Okay, so I'd like to take this opportunity to welcome you. This is not working. I'm going to just stand over here. And is this the keyboard for that?
Yeah.
This one's not working. Nothing's working. No, it's not working.
Try now. Just the arrow.
Yep. Okay. All right. Okay. So I'd like to take this opportunity also to thank the members of my group, and they basically made this all possible for me to go around the world and talk about our work. There are several of them, some of them in green. They're the ones that contributed to this work. They come from various parts of the world, as you can imagine. We're a typical group in the United States, doing research. We work on a number of areas in magnetism, and today my focus is going to be in this lecture on magnetic nanoparticles for nanomedicine applications and specifically for cancer therapies. That's what I'm here to tell you, that we can use magnetic nanoparticles for killing cancer. It's a viable technique, and we're pretty excited about it. And it's close to probably getting to a stage where this should be transitioned to the clinical part pretty soon. Like many other magnetic materials labs, we do a variety of experiments. We have a superconducting magnet. I think you heard about that from Ron, which is used a lot in making magnetic measurements or a wide range in magnetic fields and temperatures. So we have what is called a quantum design PPMS, physical property measurement system. Many of you might be using it already in your labs. So that provides us a platform. And what we do in my group is we actually build user experiments. We make our own inserts, fit into the PPMS, and we do some user experiments. And today I'm going to talk about two such experiments. One of them is the radio frequency transverse susceptibility, which is a very good, precise way of measuring anisotropy. So that's one of the things. Remember that today's mantra in this talk is anisotropy. I was born in India, we have mantras, right? So today's mantra is magnetic anisotropy. So by the time you leave this lecture hall to lunch, I hope that some of you will be chanting anisotropy as you walk away. So I'll tell you how to measure anisotropy very precisely using this radio frequency resonant method. And then another experiment that I will focus on, I wish I had a pointer, is SAR for hyperthermia. So in other words, that's how we're going to kill cancer cells, by generating heat using magnetic nanoparticles. Okay, so that's something we need to quantify, and in the community, we call this the specific absorption rate, and that's the SAR, and I'll tell you how we measure the SAR, and which is something that is useful for cancer therapy. Okay, so the outline of my talk is as follows. That was my student. So basically, I'll tell you about magnetic anisotropy, some fundamental aspects of why it is important, why we should tune this, and then the main part of this talk is going to be on anisotropic nanoparticles for biomedical applications, and yeah, we'll be dancing with the SARs. So that's what I hope to get to towards the end of the talk, that indeed SAR, which is the specific absorption rate, which is a figure of merit for cancer therapy, for example, magnetic hyperthermia, and I'll tell you how we can improve it and go beyond the current state of the art. Okay, so that's my task today. So what is magnetic anisotropy? And Ron already told you about the various exciting ways in which you can think about anisotropy, different types of magnetic materials, soft and hard. So the best way to understand anisotropy is through an equation. Like many of you, I'm a physicist. I have to show at least one equation in my presentation. So this is my equation slide, and it's a very basic equation. It basically, what it does is that if you take a magnetization vector, of course, magnetism is rooted in quantum mechanics, as you know, but I don't have time to go all the way down and explain spins and everything. So if you think of the magnetization vector, and essentially if you apply an external field, you have a competition between the external field. At large fields, the Zeeman energy dominates, so that's basically your first term there. And then as you reduce the field, the internal magnetic energy takes over, so the magnetization direction depends on the competition between these two energies. You minimize the energy, and that's how you get the direction of magnetization, right? And this explains why you have an easy direction for magnetization and also a hard direction for magnetization. And basically, this explains the shape of your hysteresis loop, isn't it? It tells you how you can magnetize a specimen, whether you need a larger field or whether you need a lower field. And that explains why certain directions are easy to magnetize, hard to magnetize. So essentially, magnetic anisotropy, that's the anisotropy energy there. I've used the simple uniaxial anisotropy, which does not have any preferred direction. We can put symmetry in there. We can take cubic crystals or other types of crystalline particles, and then you can put in the different types of geometrical, possibilities, okay? So essentially, the idea is that magnetic anisotropy is what controls the shapes of the hysteresis loops. And this is why we need to be able to tune this, use it to benefit, generate different types of hysteresis curves, specifically for the biomedical application that I'm going to talk about. So that's what we are going to look at. All right, so, okay, so we can throw in cubic symmetry, for example. So that's one thing that's possible. Thank you. But when it comes to nanoparticles, life is a little bit different because you have to deal with various types of properties here. For example, surface. Those of you, how many of you are working on nanomaterials, nanoparticles? Quite a few, all right? So you're all surface scientists. Because it turns out, as you know, nanoparticles, most of the physical properties are governed by the surface atoms. So essentially, surface, engineering the surface of these nanoparticles is important for tuning anisotropy or any other kind of magnetic properties, and especially changing the hysteresis loops, right? So that's one way to do that. You can think about shape, that's pretty obvious. You can make nanorods or nanowires where you have a preferred direction for the magnetization to align, which is along the longitudinal axis. So that's one way of tuning the anisotropy, so to speak, and essentially changing the shape of the hysteresis curves. Strain is important. You can take two materials, for example, that are in contact with each other, and the strain from the one material can determine the pinning of the spins or magnetization direction in the other material, all right? So magnetoelastic properties are important and should be able to tune these materials. Configuration, I'll get to that later on. Turns out that with nanoparticles, you can make these tightly coupled clusters, tiny clusters, and using the geometric configuration, you can actually look at the possibility of tuning anisotropy. Last but not the least, exchange coupling or exchange, what exchange anisotropy. Essentially what Ron mentioned towards the end, if you take an antiferromagnet and a ferromagnet, and at the interface, because of the difference in anisotropy, you have spinning at the interface, and essentially you can change the hysteresis loops. The coercivity can be increased, and also you have the shift in the loop. This is the so-called exchange bias that you may know about. Exchange bias is very important for the spintronics community, the MRAM community. The spin valves, for example, are based on exchange bias. Today, I'm going to tell you that exchange coupling or exchange bias, exchange coupled systems are equally important for nanomedicine applications. All right, so it's interesting that essentially the same kind of physics is important for hyperthermia or biomedical application. Okay, so it turns out that anisotropic nanoparticles are omnipresent, ubiquitous is the word that comes to mind. Turns out that it is easier to make anisotropic nanoparticles than isotropic ones. And to give you an idea, I'm going to show you 3 TEM images. They're all the same material, iron oxide, magnetite that you heard about, and ferrites, different forms of iron oxide. And you can look at them, they're all anisotropic. In this case, you have some kind of a chaining here. These are faceted nanoparticles, and again, you can see that they're not isotropic, they're anisotropic. It's the source where these images come from is what makes this interesting, all right? So how about the first one? Let's start with the left here. Can someone tell me what this is? It's a TM image, of course, of what? Bacteria. Well, if I had some candy, Ravi had given me, I would throw you one and say that's the right answer. Yeah. So what you have here, these are magnetotactic bacteria. It turns out that there are these bacteria, magnetosomes, that produce iron oxide, magnetite nanocrystals, and chain them up like these short chains using dipolar coupling, right? And what they're doing is exactly what the Chinese did when they decided, when they saw lodestone, they said that, we'll make a compass out of it for navigation. So these bacteria are doing exactly what the Chinese did. They're making tiny compasses for navigation towards a source of food. That's what they're doing, okay? Now, the second example is out of this world, literally speaking, because what you're seeing here are the same magnetite iron oxide nanoparticles found in a chunk of meteorite from Mars that crashed into the Arizona desert, all right? So you can see various sources where you actually have these nanoparticles. By the way, for the students, if you want to know about the history of nanomagnetism, it turns out that in the 1930s, when the field started developing and the word super paramagnetism was introduced, it was not done by physicists or chemists or engineers. It was done by geologists. They were the first ones that started studying rock magnetism, paleomagnetism, and that's how the field of nanomagnetism can be historically that's how it all started. The interest in these nanoparticles. The third is an example from a colleague and a good friend of mine from Carnegie Mellon University in Pittsburgh. This was from his lab. He uses a microwave plasma method to produce these kind of anisotropic nanoparticles. Again, I just wanted to show you how you can find nanoparticles, anisotropic nanoparticles everywhere in nature. You can make them. Let's now try to see if you can utilize them for biomedical applications. But okay, just to summarize, there are 2 or 3 different main types of anisotropies that we are dealing with nanoparticles. We have what is called the shape anisotropy. This is what I mean. We can make nanorods. I'll show you several examples of how we can do this using chemical methods, facile wet chemistry synthesis that we do in my lab, as well as many other groups. And then when you talk about surface anisotropy, you can actually change the nature of the surface, right? You can make these exotic octopods in this case. You can actually increase the surface area, and essentially that can create new kinds of properties that I will show you will be useful for these applications. Okay, I talked about anisotropy. I hope by now you're sold that, okay, anisotropy is important. Let's now try to look at a way to measure it. There are many ways to measure anisotropy. You can do what is called ferromagnetic resonance. You can do MOC. Many techniques are possible. But what I'm going to talk about is something that we many years back introduced. And this is basically based on a resonant method. It's called transverse susceptibility, and it's done using a radio frequency tunnel diode oscillator. So here's a schematic of the setup here. So essentially, the transverse configuration is because this whole thing is placed in a PPM. It's just a coil, and it's an LC tank circuit, right? And it is connected or driven by a tunnel diode. Now, those of you that, if you remember your AC circuits, you know that tunnel diode characteristics, it has a negative resistance region, right? There's a region where you apply a voltage bias and your current is negative. So if you bias the tunnel diode in the negative resistance region, it acts as a power source for this oscillator and keeps it self-sustained. So you can build very stable, ultra-stable, self-resonant oscillators, tunnel diode oscillators at radio frequencies, megahertz frequencies, okay? So that's what we do here. We put the sample in there, and the transverse configuration is because the DC, this whole thing goes into the superconducting magnet, so we can change the external magnetic field and temperature and measure the resonance frequency shift. So all we do is stick in a frequency counter and measure the shift in the resonance frequency as a function of external DC field and temperature. The transverse geometry is because the DC field is perpendicular to the small modulating RF field on the sample, all right? Now, this is not uncommon. Basically, your ferromagnetic resonance experiments are based on this crossed field geometries, or even NMR, nuclear magnetic resonance, is based on this crossed field or transverse configuration. Okay, that's what we do here. So what we measure is the shift in the resonance frequency of this resonator. Don't bother about the Q because the Q is lousy. It's an open coil. Q is 50. Okay, so we just measure the shift in the resonance frequency, and from that we can extract the change in the so-called transverse susceptibility. In the next slide, I'll explain to you why we do it in the transverse way. Why not do the conventional susceptibility, right? Which is just as defined by Ron, M over H, or first derivative of magnetization with respect to field, all right? We can look at that, the difference between transverse and longitudinal. One thing I want to mention is that this is a very precise and sensitive method, and the precision comes out of the fact that you can measure shifts of the order of a few hertz in an overall resonance of 25 megahertz. You do the math, you can get parts per million resolution when it comes to looking at very fine phase transitions as a function of magnetic field or as a function of temperature. So that's what gives us the precision. Students, especially experimentalists in the audience, should know that frequency is perhaps the most accurately measurable physical quantity. Ideally, you want to convert any kind of measurement, physical quantity measurement, and do a frequency measurement, and then get your essentially your sensitivity is much higher. So that's what we do here. Okay, so why transverse? And for this, we were motivated by an old paper by a famous theorist, Amichai Maharoni, from Israel. Back in 1957, he published this in the Bulletin of Israeli Physical Society. It was a little difficult to get, but here it is. That's his original graph, original plot. So what he did was he did a simple t equal to 0 calculation for a single domain nanoparticle. It's basically a Stoner-Wolfach particle, okay? So what he did was he calculated analytically the parallel as well as the transverse components of the susceptibility of this particle. And this is his plot here. So what you have here, this is a reduced field with respect to the anisotropy field, of course. As I said, anisotropy field is the most relevant field for a magnet, for a ferromagnet. And so what is plotted here is from positive to negative saturation. You see that this is the parallel susceptibility, which is nothing but taking the first derivative of a hysteresis loop, right? MH loop. So if you get this, you see that as you change the polarity, go from positive to negative, you see a singularity, a singular peak, as you would expect, because that's the switching field. That's where the spins switch. It's like taking the first derivative of your MH loop, right? Hysteresis loop. So when you reverse the polarity, you see the switching field. Then he noted that if you look at the transverse susceptibility, this is actually a tensor. It's the projection of the magnetization in the transverse direction. And he noted that in addition to the switching peak, this peak here, you get two other peaks that are symmetric, and they happen to be at the anisotropy fields. And this is precisely what we set up with our experiment to try to look for these peaks. because from these we can extract the anisotropy fields, and from that we can get the anisotropy energy, anisotropy constants, anything that you want about ferromagnetic materials. Yeah, we've been seeing these peaks for more than 15 years now, right? So let me show you some examples of how we do this with this experiment. So this is, for example, a lanthanum manganite film, calcium manganite film. Since it's a thin film, the directions are well defined, so the peaks are very sharp. So you can see these are the anisotropy peaks here. You can actually read off the values, and from that you can find out the anisotropy constant for this material. For nanoparticles, here's an example of what we can do. Remember, this thing is in a superconducting magnet, so we can change the temperature and the external field, and you can actually get in an HD plane the entire dynamics, magnetization dynamics, the switching as well as anisotropy, how it changes as you go from the super paramagnetic state, and here's the 1/T dependence that Ron showed you, and then the block state, okay? So you can actually follow the magnetization dynamics as you go across the transition very precisely. So this is a beautiful way of measuring anisotropy. Okay, so now you know anisotropy is important in nanoparticles, and we have ways to measure them accurately and precisely. Now let's switch gears and now ask the question, how do we apply this to biomedical applications, the nanoparticles themselves, okay? All right, if you want to think about magnetic nanoparticles that are currently being used, researched in biomedical applications, there are many areas that come to mind. Let's start with this one right here. These are some cartoons here that show typical areas in nanomedicine that particles are being applied. One of them is targeted drug delivery, okay? So this is basically, nanoparticles can be used as navigational aids, where you can functionalize the particle, attach drug, for example, drug molecules, and then non-invasively with an external field, magnetic field, you can use them as navigational aids, as ships carrying the drug payload, and deliver it locally to the area that needs the drug, okay? Infections or tumors, for example. So that is targeted drug delivery. Compare this with what we do right now. When we take a pill or when we take an injection, a shot, the drug is coursing through your entire circulatory system. So it's a systemic delivery. And because of that, you have side effects, right? So the whole idea of site-specific drug delivery is to avoid side effects and treat only the area that needs to be treated, especially in tumors, for example. So this is an area, we don't work in this field, but there are many groups that are actually working in this area of using nanoparticles, functionalizing them, and using it for site-specific drug delivery. Now here's an area that we also work in, and this is basically, you can use magnetic particles to enhance the MRI images, contrast of MRI images. As you know, MRI is a very common tool that's used in hospitals for brain scans, tissue scans. The way it works is based on the principle of nuclear magnetic resonance, NMR, right? So essentially, you think of the proton, water proton, and then you're exciting it with a high frequency signal, and basically the moment the nuclear spin starts processing, water proton starts processing, then you remove the field, and then it relaxes, okay? So from this relaxation time, there are two time scales here, T1 and T2. I don't need to go into the details, but from the T2 relaxation time, for example, you build these kind of images. That's the physics behind, that's the principle behind MRI images that we now have. Now, if you take magnetic nanoparticles and put it into the same area, the tissue, where you're doing the MRI scans, turns out that the fringing fields from these nanoparticles interferes with the relaxation process. So it basically increases T2, it slows it down, the relaxation. And from this, one can have an enhanced contrast of MRI images. So this is a very well-established area, lots of groups, lots of nice results coming out of this. So it's known that magnetic nanoparticles can be useful for improving the MRI contrast in these images. I'm going to skip this cell separation. You can use it for separating different biological entities, but the focus is going to be on using these magnetic nanoparticles without attaching any drug or anything like that, just using the particles themselves for generating local heat and killing cancer cells. This is called magnetic hyperthermia, and the rest of my talk is going to focus on how do we do this and how do we improve this, okay? So as the name suggests, cancer cells do not like to get hot. And it turns out that all you need to do is increase the temperature, the local temperature of the tumor, just a few degrees Celsius above your normal body temperature. So the window here, the therapeutic window, is 40 to 45 degrees Celsius. So you need to be able to increase the temperature, get to this window, the therapeutic window of this temperature range, and then hold it steady for about 30 to 40 minutes, which is typically the treatment time for patients, and cancer cells die. Cancer cells do not like to get hot. They hate Florida, okay? So we need to generate Florida temperatures, and that's what we do. So the point is that if you're, I'm not a biochemist, but essentially this is what happens. You have protein denaturation, the cell membrane. You need to rip apart or break the cell membrane of the cancer cell. That's what we need to, that's the goal of all of us, okay? So essentially what happens is that after the cell membrane restructures, eventually the cell dies. It is driven to deactivation. This process, we call this apoptosis. Apoptosis, if you want, think of it as a benign, friendly way of killing cancer. The opposing side, the other example is necrosis. Necrosis is a brute force, aggressive way of killing cancer. Do we have examples of necrosis? Sure we do. That's what we do in hospitals. The most effective forms of therapy, chemotherapy, radiation therapy, they're all, you can classify them as necrosis because guess what? They're very effective, but there's a lot of collateral damage, right? The body immune system breaks down, for example, and you have a lot of side effects. And those of you that have either cancer patients in your families or among your friend circle know the visible changes that the patients go through when they're undergoing chemotherapy. So I've been asked this question, is this magnetic hyperthermia, which is relatively benign, is it going to replace chemo? The answer is no. But it will be an excellent supplemental technique that will be, in addition to chemo, if you can use this as a supplemental technique, you can actually reduce the chemo dosage, you can increase the time between chemo dosage, so essentially it improves the quality of the patient's life, in addition to keeping the treatment going. So that's where magnetic hyperthermia is going to be effective and will be very effective as a therapy. Now, I'll give you the good news and the bad news. The bad news is, there are 3 letters that we have to deal with here in this country, and there are other analogs in other countries. In the United States, it's called the FDA, the Food and Drug Administration. For very good reason, the process of approving any new kind of therapy is very slow. For good reason, because we're talking about human treatment for humans, right? So if you want to put something into the human body and for getting clinical trial, getting it to clinical stage, transitioning it to clinical trial takes a long time because of the FDA process. So we don't have approval for human testing yet. The good news is some of you from Europe, you guys are way ahead. Turns out that there's a company which has been around for a few years now, MagForce, it's based in Berlin, and it turns out that they have got the approval from the European Union and millions of euros to do this research, and they're actually doing clinical testing with patients, human patients, this technique of magnetic hyperthermia, all right? And they're getting very successful getting good results. So eventually we hope that this is a path for the future where we get the approval process, and this technique is going to be one of the techniques that's available for hospitals around the world. Okay, now the way it works is simple here. As I said, the way you do it is you take these nanoparticles and switch from a DC field to an AC magnetic field, a large amplitude AC field, high frequency magnetic field, and that's how we generate heat. Let's look at the basic principle of how this happens, okay? And the reason why I spend a lot of time talking to you about anisotropy and hysteresis is because this is what we're going to use to generate heat, hysteresis loops. And hysteresis loops that look like this, we want a large area. Remember that area inside the hysteresis loop is dissipation. And dissipation here is in the form of heat. So we want to increase the area inside the hysteresis loops by playing around with different conditions, namely the external field that we apply, external frequency, as well as the types of particles that we use. I want to point out something very carefully. Remember, these are very small particles. We're talking about nanoparticles, and as you know, most of them, if you go below a certain size, they are super paramagnetic, so there's no hysteresis, isn't it? But that's the DC hysteresis. That's what you measure in a squid or a magnetometer. Don't confuse that with this hysteresis here. This is the AC hysteresis loop. Here, the hysteresis, think about it this way. You have the magnetization. Each particle is a super spin by itself, super paramagnet. Okay, it has a large magnetization. It tries to follow the high frequency, several hundred kilohertz, for example, high frequency. It tries to follow that. It cannot. It goes out of phase. And that's how you get this hysteresis loop. So you want AC hysteresis loops to be optimized to improve the heating. Okay. And like any other technique, you need a figure of merit. The figure of merit that is used here is called the SAR, specific absorption rate. And you can think of a very simple definition of this as the area of the hysteresis loop multiplied by the frequency. So clearly we can change the frequency, we can change the field amplitude, the AC field amplitude, and also we can use nanoparticles that have a large saturation magnetization. All these will improve the SAR, okay? Now the question is, can we just do any of these and play around and optimize the conditions? Because keep in mind that ultimately these are particles that are going to be put inside the human body. So we want to reduce the number of foreign particles. So we need to generate a large SAR with a small amount of particles, small volume of particles, and find the right conditions to do that. Okay, so I'm sorry, I said one equation slide. This is my second one. This makes it easier to help you understand what we mean by this power here. The power dissipation is related to the product of the field and the frequency. There are also some time scales involved. Remember that these particles and movements are trying to follow the high frequency. So the two time scales typically used here goes into this equation are tau b, which is the Brownian motion, Brownian relaxation time, and tau n, which is the Néel relaxation time. For example, when you apply an AC field, if the particles are free to move, if the environment is more like a liquid, for example, then you have the Brownian motion, right? So that leads to the Brownian relaxation time. And then, of course, if the particles are in a cell which is viscous and you don't have the motion of the particles, then it's basically the Néel relaxation time, which is the magnetization vector that follows the high frequency. So ideally, if you want to improve the SAR or the power dissipated, you can, first of all, you can increase the saturation magnetization of nanoparticles. Easier said than done, because you know that you need to prepare very high quality nanoparticles to get large magnetization. There's also a size dependence that one of the things I want to mention about the size dependence is that for effective hyperthermia, it should not be too small or it should not be too large. It turns out that the sweet spot is when the particle size is somewhere close to the single domain to multi-domain transition, okay? So we are talking about 30 to 50 nanometers. That's about the size of the particles for iron oxide that we're talking about. Why not small? Why can't we use particles that are less than 10 nanometers? It turns out there's a big health risk here. If you take very small particles, the chances of these particles penetrating the so-called blood-brain barrier is high. So instead of going to wherever you want, they end up going to the brain. That's the wrong place you want your particles to go to. Ideally, you want these particles to do their job, heat up, kill the cells, and after the job is done, you want it to be flushed out of your body, go down south to Florida, all right? So that's what we want. We want to heat it up, heat it for a certain amount of time, 30, 40 minutes for the treatment to work, and then flush out the particles. Ideally, that's what you want to do, and there are several constraints for doing that, and we'll go over some of these things. Anisotropy, now that's something that was not really studied for many years, and this is where our group got in, and we thought that since we are anisotropy jocks, we can measure it, we can make anisotropic nanoparticles, so let's look at the correlation of can we improve SAR through playing with the anisotropy, all right? So I'm going to use several examples of how we can do that. The other thing that we measure in the group, we need to measure is the SAR itself, the heating efficiency of these particles. How good are these particles in heating up the cancer cells? So for this, we do two different techniques for magnetic hyperthermia. We use a calorimetric method in our university, in my lab. And you can see that that's the AC power supply. Remember that we need to generate high frequency, large amplitude fields, not small amplitude, okay? For example, when you do AC susceptibility in your squid, in your commercial squid that you use or quantum design system, you're working with very small amplitudes, okay? So here we need to generate hundreds of Oersted in amplitude for the AC. That's quite challenging. That's why you need large power supplies for that. So what we do is here's the power supply here. So we basically that's the coil. The particles go in there, and essentially we directly measuring the change in the temperature by using a temperature sensor. So we measure the increase in temperature as a function of time, and our data looks like this. This is what it is. Basically, what we're doing is, remember, that's the therapeutic window, 40 to 45 degrees Celsius. You need to heat it up to 40 to 45 degrees Celsius and hold it steady for a certain amount of time. And if you look at this is for manganese ferrite nanoparticles. I'll also show you results for other systems. So this is in this case, our power supply works at a fixed frequency of 325 kilohertz. Okay, that's the frequency of the power supply. And we can change the AC field amplitude. For example, a few hundred Oersted here. You can see from this, for these particles of this size, the ideal conditions of hypothermia are met when your field amplitude is about 500 Oersted at this frequency of 325 kilohertz. So that's how we can fine tune the external parameters like the frequency and field to be able to get to this window. Remember, that's what ideally you don't want to overheat. There's no reason to overheat. Of course, if you don't supply enough power, they don't heat up. So in this case, this reaches the condition for hypothermia, and you want to stay there, you want to saturate there. The saturation process is simply through thermal equilibrium with the surroundings, okay? So in each case, this will differ. So you need to tweak the parameters to get the SAR, the correct conditions for hypothermia for the treatment. All right, so we make these nanoparticles. We also measure SAR through a different way. And for this, we work with collaborators in Spain, University of Basque Country, for example. And they have built a huge AC power supply using a capacitor bank. They can generate a large amplitude AC supply. And essentially, they can measure the hysteresis loop at high frequency. So they directly measure. So we make these nanoparticles, ship it to our collaborators in Spain, and they generate and measure the hysteresis loops. And they get the SAR from that, from this expression, right? You can actually get the SAR also from the hysteresis loops. So they do this on the same sample. Now here, this is where I tell students a certain tip. If you want to publish your paper these days in physics, for example, in a high impact journal, ideally, like Nature Physics or PRL, for example, ideally, if you want to prove something, show a result, you need at least 2 different experiments converging to the same result, okay? This is almost a requirement these days if you want to show this. This is what we do here. We want to get the SAR, optimize the SAR, and make sure that it's reliable by doing 2 different experiments to measure the SAR. And not only 2 different experiments, 2 different labs, 2 different countries. Even better, right? So this is the importance of international collaboration cannot be overemphasized here. It's important for us to work together and combine our expertise in making sure that we are taking these things ahead. Okay, now I keep saying that we cannot, there are limits to the frequency and field that you apply. You cannot arbitrarily apply megahertz frequency or increase the amplitude to Tesla fields. Why is that? There are limits, and the reason why we work with few hundred kilohertz in terms of frequency and a few hundred Oersted at most in terms of field amplitude. And this is because of, again, remember that this treatment is for humans, so they need to be subject to this condition for an extended period of time, for an hour, 40 minutes or so is the typical time. So which means they need to experience these conditions of high amplitude, high frequency, okay? And think of this as a pain threshold, which I can't see here at the bottom. It's there at the bottom, but it's hidden, but it's called the Atkinson-Brezovich limit. You can't see it here because it's right there at the bottom. So it's the product of the field amplitude multiplied by the frequency that determines, and there's an upper limit to it. You cannot exceed that. Think of it as the pain threshold, right? So what is the pain threshold? For example, in the United States, if a patient goes to an emergency room, the first person that meets the patient, we call the person a triage nurse, he or she. One of the first questions they ask is, on a scale of 1 to 10, what is your pain level? And of course you say, must be the same in most countries anyway. So then you say it's 2 or 3, or if you're close to dying, you say 8. So that's what we mean by that. So we need to keep the treatment, the conditions, namely the upper limit for the frequency and the field below certain values so that you don't cause any nerve stimulation and things like that. So that's the reason why you have to be very critical, very careful about these values. Okay, but again, don't worry about your cell phones, because cell phones at 2.5 gigahertz, very high frequency, but yeah, the power is too small. So no, they're not going to catch fire when you pump gasoline, okay? So it's the power that's critical here. All right, so what can we do now? Now that we can tweak the external parameters, like we can change the frequency and the field amplitude very easily. So the only thing that remains is, can we do something to the material itself, to the nanoparticles that are used for this treatment? Here, we have a severe limitation. Again, thanks to those 3 letters that I mentioned, FDA. It turns out that the only magnetic material that's been approved for this treatment is iron oxide, magnetite, maghemite, that's it, period. You cannot use exotic materials that you make with large saturation magnetization, and cannot use it for hypothermia because they are not biocompatible. The only biocompatible material we need to work with is iron oxide. So there's a severe limitation. So whatever I'm going to talk about next is see what we can do to the basic magnetite, iron oxide, and see how we can improve it further, the SAR. Well, if you look at this graph here, you see that unfortunately, iron oxide is very low. This is the SAR plotted as a function of saturation magnetization. Ideally, you would like to work with iron. Iron cobalt is even better, but you can't. They're not biocompatible. You're not allowed to use that. All right. So, but then, well, I talked about the size dependence. Anisotropy is a mystery. Can we do this? And this is where I would like to show you that indeed you can tune the anisotropy and improve the SAR. But first, can we fool the cells? In other words, can we make a core shell system where we have a core which is iron, which has a larger saturation magnetization, and a shell made of biocompatible iron oxide. Completely encapsulate the iron so that it's a core shell, but large, effectively large saturation magnetization. We and many other groups thought of this, and we tried to do this, and I'll show you some results. This is the idea. Again, Ron, I would stick with EMU program. You know, I'm a physicist, all right? Who doesn't like EMU? Nice birds. Okay. So, for example, you see that iron oxide is 92 EMU program, and iron is 220. So if you make a core of iron and encapsulate it by iron oxide, you have a core shell system with a large saturation magnetization. So here are some TM images of core shell particles made in my group. Over the years, I've had the good fortune of working with a number of excellent postdocs and students who are well-trained in chemistry. You need excellent training in chemistry to make high-quality nanoparticles. Making nanoparticles is relatively simple, but making high-quality single crystalline nanoparticles is what is needed for improving SAR or any other type of application. Okay, so those of you that are interested in chemistry, what we do here is very simple thermal decomposition. That's what we use in our lab, and many other groups use this. Essentially, you can control the particle shapes and size and the growth process by playing around with the temperature of the reaction time, and also the surfactants that you use for the particles. Well, we tried the core shell with the iron core and the iron oxide shell, but it turns out that there's a problem which is known as the Kirkendall effect. This has been known for metallurgists for many years, since the 1940s. By the way, the word metallurgy has almost disappeared. It's all morphed into material science now. When I was a PhD student, I remember there were departments of metallurgy. You don't see them anymore as much. They all become part of material science. So this Kirkendall effect is because, you see, iron core, iron oxide shell. Because of the differential diffusion of the metal ion when compared with the oxygen ion, there's an instability of the interface, and this causes voids to open up, holes to open up. And over time, these holes get bigger and bigger, and ultimately the iron inside oxidizes, and essentially you get a thicker shell of iron oxide. It becomes a hollow nanoparticle. So if you want to make high quality hollow nanoparticles, this is how you do it. But unfortunately, this is a problem for hyperthermia, because as a function of time, your system is changing and the magnetization is changing. So it's not very reliable. So we did some studies on this, and we can actually follow the whole process. These are TEM images, and we did the magnetization dynamics to study how the magnetization evolves. But let me show you the data here. I'm going to show you the SAR data as histograms here for easy comparison. Let's look at the right-hand side here. So if you look at this, you can see that the proof of concept works. In other words, if you make a core shell particle with a larger saturation magnetization compared with the same iron oxide particle, always the core shell has a higher SAR, as you would expect, because you have increased the magnetization. So it does work. In every case, you see that the core shell particle is better than the solid particles for heating up. However, as a function of time, you can see this shows the function of time. Our happiness was short-lived, precisely a few days to a few weeks. And this is undetermined. We don't have control over this process. It depends on various conditions where these particles are being synthesized. All right. So essentially, we don't have a control of this, but we can see that the SAR drops. So, and when you end up with hollow nanoparticles, there's no SAR. There's no heating at all. So unfortunately, we had to discard this. However, we thought that core shell is the way to go. That's the way to go, except that you can make metal oxide. It has to be all oxide so that there's no problem with Kirkendall effect or differential diffusion. So while we were thinking about it, as I said, it's a story, right? We're progressing slowly to the next part. While we were thinking about it, there was a group in Korea that made these exchange couple core shell particles. And this was published a few years back, and they scooped us in some sense, but they had the right idea here. This is all oxide. This is cobalt ferrite, manganese ferrite, nanoparticles, core shell particles, and they showed actually the exchange bias in these systems, and they showed that basically these are excellent. They show a large SAR. They show very good heating for hypothermia. Okay, but then look at this. We looked at that cobalt ferrite, manganese ferrite. Cobalt is poison. FDA doesn't want to listen to the element cobalt. They don't want the cobalt to be put in at all. Okay, so cobalt is poison. We can't use it. So we thought this would be a horrible process to try to get this approved through the FDA. So let's stick to something that they already have approved, which is magnetite. So can we make a system, core shell hybrid system like this, all oxide with magnetite as the outer shell, because that's biocompatible, right? So we did that, And we made this system here. This is exchange coupled, and look at the exchange bias for these nanoparticles. They're like tiny spin valves here, nano spin valves, okay? So this basically is an inverse core shell. Turns out Fe3O4 magnetite has to be the shell because that's the biocompatible iron oxide that's been approved. And inside you have FeO. FeO is a lesser known phase of iron oxide. It's the Wüstite phase. It's antiferromagnetic. So what we have here is an antiferromagnet and a ferrimagnet outside. So essentially it's an exchange coupled system. You can see the exchange bias, and indeed this one was really good for giving us a high SAR, okay? Now at this time I have to tell you that in my group we have these, as I said, very talented postdocs and students, and often we have a sort of internal competition among the group members, and we basically, whoever makes the highest quality mono-dispersed particles, they are given the title of a wizard, Harry Potter, for example. And if it's a lady, it's a Hermione, okay? So in this case, Hafsa was definitely the Hermione that year, because what she did was she made these core shell particles, and then on top of that, she changed the shapes to study the anisotropy. Remember that we wanted to correlate the anisotropy with the SAR. So this is done by the same kind of a method. And so essentially what she did was she went from nearly spherical particles to cubes to these octopods, these star-shaped particles for the same system, for the core shell system that I talked about, where the shape is also changing now, all right? So to do a systematic comparison of the SAR and how it changes with the anisotropy. The next slide that I will show you is probably the most important of this presentation because it gives you the message very clearly. And yes, this is what I mean by dancing with the SARs. We need to change the shape anisotropy to improve the SAR. So here's the correlation: spheres, cubes, octopods. Again, look at this. This is the histogram here. Definitely, as you change the particle size shape, go to a lower symmetric system or a high anisotropy system, the SAR is increasing. In fact, we found out that the SAR increases even more than trying to improve the saturation magnetization. So indeed, anisotropy is a key parameter that you need to tune to be able to get high quality particles for magnetic hyperthermia. So this is one of the main messages that we have here. So we got excited. Obviously, we can do a lot of things, right? We can make, then we thought that let's go back to the bacteria. They make these nice short chains. And it turns out that these bacteria were studied by our collaborators in Spain. They actually measured the SAR. They found really impressive SARs for these bacteria themselves, okay, with the short chains. It's almost like the bacteria are giving us a clue, biomimetic clue, to make these kind of short chains. So since these are magnetite chains, by the way, so they're biocompatible, all right? So since they did the chains, we thought we'll try to do nanorods, extended nanorods of the same kind of, change the aspect ratio, and we did that. For this, we used a technique called hydrothermal technique. This is like a pressure cooker. You can cook particles of high aspect ratio. In addition to the time and temperature and the surfactants, you throw in pressure as a variable, and you can actually get very good, high quality, high aspect ratio nanostructures, nanorods. And I'm going to wind up in a few minutes. We're almost close to the to finishing up here, so that I can have some time for questions. So essentially, we can play with the aspect ratio here, change the length and to width to some extent. We compared the SAR with the aspect ratios of the magnetization, and indeed, the good news is that these nanorods are giving us really high SAR, quite high, very respectable SAR. So again, making the case that you change the anisotropy, and that has a direct influence on the hyperthermia potential. Here, I should emphasize with this slide here that you need to make high quality nanoparticles. That's what it takes. You need to try to get the highest saturation magnetization. In fact, you can do this. You can almost get magnetization close to the bulk value. Here's an example. This is the magnetization for these nanorods, 86 EMU per gram. Compare this with the bulk, which is 92. We're almost there. So you can make highly single crystalline nanoparticles, and that's how you get the highest saturation magnetization possible for your systems. That's why you have to pay a little attention, work a little harder, make high quality particles. This is the message if you want to increase the SAR in this case. In magnetite, you can also do a quality check, whether your magnetite particle is high quality or not. Turns out that Fe3O4 magnetite has a celebrated metal insulated transition. At low temperature, 120 Kelvin, it becomes, basically because of a phase transition, it's a first order phase transition, it becomes from a metal to a really good insulator, a huge metal insulated transition. And because it's a first order phase transition, there's a signature in the magnetization, you see a change. Here's your Verbe transition for these nanorods. If you make particles of lesser quality, you will never see this. You'll never see the word-wave transition. So this is a good quality check. If you're making magnetite nanoparticles, look for the word-wave transition. If you find this, it's likely that you have very good, highly single crystalline particles, and that's what is needed for the applications. Okay, so what else can I tell you? It turns out we're right now working with this system here, Fe3O4 cobalt ferrite, but Fe3O4 is covering it completely, so it's all hidden inside. The reason why we chose cobalt ferrite is because among the ferrites, cobalt ferrite has the highest magnetic anisotropy. So if you're playing the game of tuning anisotropy, this is a good system that we wanted to study. And again, it's showing very promising results. Something else that I have to tell you is that not just magnetic hyperthermia, it turns out that metallic nanoparticles can be used for heating up locally. Like gold nanoparticles or silver nanoparticles, if you make them like 10 nanometers, you can heat it up locally. And here, this is because of exciting the so-called surface plasmon resonance. You can shine a laser and heat it up, all right? So we tried making these hybrid particles by connecting gold and magnetite, or in this case, silver and magnetite. Gold is even better. Turns out that the lattice constant, if you look at gold and magnetite, they differ by 2. So you can have epitaxial interfaces, high quality interfaces, okay? So in this case, the idea was to keep both of these particles, the surfaces exposed for functionalization. Gold has its own thiol chemistry, can attach various molecular ligands and things like that. Remember that the magnetic particle is just the basic entity. We need to have surfaces that are completely covered by biocompatible, materials, molecules, and also you may want to attach certain molecules so that you can tag specific cells. Right? So there's a lot of biochemistry that goes on. So for that purpose, we need to keep these surfaces exposed. So instead of covering the particle, magnetite, completely with gold, making a core shell, we made these kind of clusters where the surfaces are open for functionalization. And again, the other idea was to try both these types of heating in the same system. It's a composite hybrid system, right? So you can apply AC hyperthermia, AC fields and look for AC hyperthermia, heat it up that way, and also shine a laser and heat the metal. So we tried these various combinations, and of course, as you might expect, when both these stimuli are present, it heats up faster. In fact, my students started playing with it. They turned on the AC field, and remember the saturation curve, come to the 40 to 45 degrees saturated, turn off the AC field, and start pulsing the laser to keep it constant. So we can do this with these kind of hybrid nanosystems. Everything that I told you so far is only half the story. But no, I'm not going to go through the rest of the story or something like that. But the emphasis that I want to point out is that any new material that you make, any new nanoparticle or any kind of material you make, you have to prove or show its biocompatibility. This is a requirement. It's not going anywhere if you don't do the cytotoxicity results. These days, if you want to publish in this field of applying nanoparticles for nanomedicine, you need to show the cytotoxicity results. Okay, it's very important because you need to prove that these particles are good to put in the human body. All right, so we have to do this in every system. I'm just showing you an example. And the nice thing here is that cells love to eat the particles, especially cancer cells. They're really hungry. They'll just gobble everything. Okay, so all you need to do is take these particles, take them to a cell culture lab, incubate them with a cell that you want, and then wait 24 hours or 48 hours. And during that period of time, you basically have the cells, completely uptaking these particles. They love to eat these particles. In fact, I was giving this talk at Banadieni at SpinTech in Grenoble, and one of his group members, one of the students from the group members, they gave me this picture, and I thank them for that. This is work done. This is just to demonstrate how the particles. This is a fast frame video taken over 48 hours of the process of cells. In this case, it's glioma cells, and those are the particles, and you can see how this is compressed, 48 hours compressed into a short video here. And you can see that obviously the cells, they want to die. They eat the particles. Let's feed them, okay? Let's feed them. The technique works. The AC hyperthermia technique works. So it's all there. We're just now waiting for the process of approval so that eventually this can be the transition to clinical trials in hospitals and human testing takes place pretty soon. We have the data and we have the materials, and so it's in the right path. This is just to show you that you can look at the cell death. The way this is done, cytotoxicity this is why we need graduate students, folks like you. You have to patiently look through the microscope and count how many cells are alive and how many are dead after a certain period of time and record it in histograms. That's how cytotoxicity results are done. Okay, so I would also like to point out that there are other ways of killing cancer cells. Remember that the cell membrane has to be ruptured, right? So another way of doing it, here are some examples of two different groups that use what is called magnetomechanical destruction of cancer cells. So in this case, they make these nanorods, for example, high aspect ratios nanostructures, and then they cleverly design it, using synthetic methods, synthetic antiferromagnets, for example, where the torque is maximized at low fields. So when you apply a low field, low frequency signal, because of the maximum torque, they start spinning around like motors, and in the process, they destroy the cell walls. Okay, so this is magnetomechanical, destruction of cancer cells. Again, the advantage of this technique is that you don't need to go to very high fields. You can apply low fields and low frequencies. So there's some advantage to this technique. It doesn't, produce intense conditions for the patients, but we do need all these techniques for cancer therapy. A bit of good news here. Remember the company that I told you, MagForce, based in Germany? They're now in the US. They just entered the United States last year, and as of 2018. And it turns out that a few months back in September, I understand that they have their first cancer patient that has signed up for this treatment here. And any new technique, there's a lot of disclaimers and waivers, and usually it's the terminally ill that would like to volunteer. So there are more patients that will be volunteering for this technique, and eventually this process is going to be in the hospital soon. My prediction is that the next 5 to 10 years, we will have this approval process, we'll have lots of clinical testing done, and it will be transitioned to the hospitals. Since many students are there, the magnetism community, we have this habit of coming up with these roadmaps once in 3 years. Okay, so the 2020 roadmap should be started soon, should be out soon. Just to give you an idea, if you want to know about what's going on in the field of magnetism, you can come to these summer schools. Of course, you're here. You can also read some of these kind of articles, review articles. I just wanted to show you that. I also would like to have you go talk to your supervisors and encourage that your paper be submitted to Journal of Applied Physics. I'm one of the associate editors for this journal. There are 3 of us associate editors that are actually in the field of magnetism. So we do publish a lot of papers in magnetism. So, and also biophysics now these days. So to summarize, because we have a popular movie out these days, Godzilla. So size does matter, but no, we're not talking about Godzilla, that kind of size. We're talking about nano size. And of course, nano size has been around for a long time. So it's not just nano size. My message here is that even in nanostructures, you have to play with the surfaces, the shapes, engineer the anisotropy. And that's the key for heading towards improving the state of the art in some of these applications, especially nanomedicine. Here are some pictures. One of my students is actually here, Richa. You can talk to her if you want to know more about Florida, Tampa, and also our lab. And let me summarize by finally, on behalf of the USF Functional Materials Lab, FML Group, as well as the IEEE Magnetic Society, I would like to thank you for your attention. And like many of you, some of our best research discussions in my group happen in coffee shops and in bars. Thank you very much.
Got a question. I think you mentioned the treatment. Well, the principle of the treatment you propose as the fact that the nanoparticles are going to heat up when they're exposed to an external magnetic field. What would you say is the key factor that makes this treatment selective in terms of the appropriate cell and not kill the right cell?
Yeah, that's an excellent question. That's why I said the nanoparticles themselves heat up, but we do have other attachments. There are specific ligands, specific molecules that can attach and target certain cancer cells. So this is well known. So there are ways to target specific cells. Okay. Now there's going to be some heating happening with the healthy cells too. And it turns out that cancer cells are more susceptible to heat, so they die faster. So that's the idea, to try to minimize the damage in that sense. Take one here.
Thank you for your report. I've got a question about transverse magnetic susceptibility technique. This technique could be very sensitive to interaction between particles, especially when some systems of nanoparticles are investigated by this technique. So how to deal with magnetostatic interaction with contribution of higher order magnetic anisotropy constants in estimating the value of anisotropy fields.
Yeah, I mean, what the technique measures the effective anisotropy. It's very difficult to separate the contributions from different contributions that go into the effective anisotropy. We can do that by doing specific experiments. For example, in nanorods, for example, you can try to align them so that there's a preferred direction. We've done that. So the way we do it is these nanorods, we use what is called typically a gel. Like you can take paraffin wax, for example, which if you heat it up, it's a liquid. Put the rods in there, apply a magnetic field, you can align them, and then you can make it a solid. And that way you can also prevent these rods or particles to move around. So we do that. We do it in gels and we do it in wax and things like that. We can get some idea about the various contributions, especially if there's a specific type of anisotropy. But in general, it's very difficult to decouple the different effects. So we measure what is effective anisotropy for the system.
Thank you.
Hello, thank you for the talk. I didn't understand very well if all core shell particles transform into hollow particles. But for those who get the transformation, which is the characteristic time?
The characteristic time that we noted in the lab, and it differs from batch to batch. That's why it's not reliable. It differs on the humidity and the conditions. And so the process, this effect itself, remember, it's something that is related to conversion of metal to oxide. Okay, so there's no uniform way in which to describe it. That's the problem, because if it is predictable, then we know that we can use these particles for a certain amount of time and have reliable SAR. When this is unpredictable, it's unreliable. It's not something we want to transition to the next stage.
Thank you.
So to precisely answer, it could be days, it could be weeks. That's what we found. Several batches.
Thank you for your presentation. I have two small questions. The first one, if I understood well, you mentioned that the best SAR is the one in the nanoparticle produced by this bacteria. Then why not use directly this nanoparticles?
Yeah, I mean, I've been asked these questions. Yes, indeed, they produce the highest SAR, but not the highest though. They produce the best SARs, quite respectable values, but they're not the highest though. There are schemes out there where you use some of these bacteria because they're one of the best types of particles that you need is the ones that are biodegradable. Unfortunately, there's no example of a biodegradable magnet right now, magnetic particle. So ideally, that's what you want. So the bacteria are also being tried. I don't know what the status is right now, but certainly the chains are important. The size of the chains, the dipolar coupled chains, they're important. Okay.
And just a small other question is that it's usually mentioned that it's for cancer treatment, but you mentioned that we need to separate the blood from, let's say, the brain one. So what if the tumor is in the brain?
Yeah. In fact, the last picture that I showed you, the work from Grenoble, for example, that's on glioma. And that was the first tumor that this technique was first tried, glioblastoma, which is a brain tumor. Okay. Now keep in mind that if you need to do this clinical trials, you need to have volunteers, and typically these are patients at the terminal stage, and they would try anything. Okay. So that's how it started. So with glioblastoma, is how it started. But be careful that the brain particles, you don't want the particles to end up in the brain for many reasons. For example, I can tell you that there are two diseases which are well known, have no known cure. One is Parkinson's, for example. The other one is Alzheimer's, right? Well-known diseases, no known cure. Statistics show that these patients have iron oxide particles in their brain. So we still don't know if it's the consequence of the disease or is it a cause of the disease. But I'm sure that some of these issues will be addressed in detail by Professor Saramatic, who will specifically talk about various issues that have come up here.
We have time for one more question.
Thanks, Professor. I have 3 questions. First, when you measure the SAR value, what's the solution did you use? And the second question is when you control the shape of the nanoparticle, it will have effect on the shape anisotropy, but the surface area will be different. Will this surface have effect on MS value. And also for the iron oxide, you use the high hydrosol method to prepare the nanowire of iron oxide. I want to know what's the MS value.
Okay,
Thank you.
there are 3 questions in there. So let me remember the first one. The first one is that, I'll answer the third one. I remember it the best. Okay, the hydrothermal technique is great for making high aspect ratio nanoparticles. You can also get very good crystallinity, single crystallinity. I emphasize that you need to be able to see the planes, crystal planes right up to the edge in a high resolution TEM. That's your check for high quality. Once you get that, you automatically have a large saturation magnetization. Okay. There's also, you have to keep in mind that it's very difficult to distinguish between maghemite and magnetite in nanoparticles. This is well known. We can't tell the difference using XRD. You need to do more experiments, Mossbar, for example, XMCD, sometimes to look at the interface. Okay.
So unfortunately, Professor Hari will be here only today. So if you have more questions, maybe you might want to catch him during the lunch. So we are already late for the lunch, so we'll break this session.
Thank you very much.